All right, so today we'll finish up section 9.2. We're going to look at some graphs in polar. We'll talk about how to convert between polar and parametric, and a few other things. Okay, so we haven't really done anything on the calculator yet with setting a window in polar, but it's almost exactly the same as setting a window in parametric. Okay, same idea. Okay, so just a reminder that in polar, we don't use xy. The point is written as r comma theta, where r is the distance from the origin, theta is an angle with the positive x-axis. Okay, so let's start with a graph, and it's a graph of r equals 2. So the easiest way to think about it is to maybe just make up some points where the radius is 2. Now, notice it doesn't say anything about the angle. So the angle can be anything. Okay? The only restriction here is that r equals 2. So could somebody give me a coordinate where r is 2? Yeah?
2 180 degrees.
2, 180. Hey, and I'll graph that. So I would go the second ring, 180 degrees, counterclockwise. There's one point on our graph, r equals 2. Could someone give me a different coordinate that would be on this graph? Jay?
245.
245, yep. So 245, there's another one. And we'll do one more, and then I think you'll kind of get the idea what's happening here. 270. So 270. Okay, so the key is right here. They're all 2. So 2 units, 270. Now, if I could graph every single possible point, what would my graph look like? Yeah, it's a circle. It's basically it's a circle with a radius of 2 centered at the origin. There's the graph of r equals 2. Okay, if you want to graph that on the calculator, this is an easy one to kind of take a look at. So first thing we do is go to mode, put it in polar, and now when you press y equals, it doesn't say y equals anymore. It says r equals 2. That's it. So you have to type in r equals 2. Now, if I do zoom 6, it's going to set it from -10 to 10, -10 to 10. If you set that as your window, what is this going to look like? Yeah. It's going to look more like an oval because you're putting 20 units left and right and 20 units up and down. Does anyone remember what the scale factor was that you could multiply the x by to make it look the way it should? Yeah, it's 1.6. So in this case, just 16. So it's probably faster to just type it in. Now, to me, that looks more circular than it did before. Remember, there's only so many pixels on the screen. It's not like 4K here. So that's the best the calculator can do. I'm going to zoom in a little bit. And when I zoom in, it should zoom in proportionally. So it should stay with that 1.6 aspect ratio. You could check it. Take 7.5. Take 4 divided by 2.5, and that should still come out to 1.6, because that's how we set it. All right, a couple things to kind of pay attention to. With this particular graph, we don't have theta, okay? It was just r equals 2. Now, if we did something with a theta, then we'd have to be careful about setting our theta step. Okay, that theta step is going to give you the resolution of your picture. And the same thing can happen here that happened in parametric. If you're trying to graph like a spiral, and your theta step is too large, your spiral is going to end up looking like this, which is probably not what you're looking for. If you want it to look like it really should, you have to make the theta step smaller, so there's not so much of a gap between points, and then it'll look like it should. What else is there? So theta min and theta max, that's just like your T min and your T max. Whenever you have something with a sine or a cosine, you usually want to go one full cycle, all right? Some polar graphs will trace over themselves. Okay, just like when we did parametric and we did circles, if you go too much, it just traces over itself. Something like a spiral doesn't. If you go too much, you're going to get more spiral. And maybe they don't want more spiral. Okay, so it depends on the picture, on the equation. Any question on that one? Okay, so let's look at this one. This is one we can't really do on the calculator because it's of the form theta equals. I can't do theta equals. I can only do r equals. In terms of like a rectangular coordinate system, this is kind of like trying to graph x equals. You can't do that. You can graph y equals and get horizontal lines on the calculator, but you can't get vertical lines. Okay, so same idea. Can somebody give me a coordinate that would be on the graph of theta equals 2? Trevor? It's kind of like the last one. You can't really, well, you can go wrong, but there's an infinite number of answers here.
245.
That would be a good one for the last one.
Yeah. 2, 2.
Sure, we could do 2, 2. Okay, that would be a point. Let's just write a bunch of them. We'll do like 3 or 4 of them. Someone give me another point that would be on the graph of theta equals 2. Yep.
4, 2.
4, 2. Yep. Let's not go any bigger than 4 with the radius, only because my graph paper is not big enough. What else? Yeah.
-2, 2.
Yeah. There we go. So now we got a negative in there. That should give us a good idea. Also, if you're not 100% sure what 2 radians is, to graph it, you kind of need to know what it is. So we could just convert it to degrees. And I think it's about 114 degrees. If I do it out, it's, let's see, 2 times 180 divided by pi, just converting degrees, radians to degrees. So it's about 114 degrees. All right, so 114 degrees is a little bit past 90. So we've got 2, be about right there. We've got 4, and about right there. And then we've got -2. So we would go 2 units to the left, and then come around 114 degrees, excuse me, clockwise, counterclockwise. Great, so what does it look like we're going to get here? Yeah, we're going to get a line. A line through the origin in polar, it's not too bad to draw. Okay, so my points aren't perfect, but it should kind of look like it goes through the origin. That's as good as I can get. Okay, but there's a line through the origin in polar, so not super bad. Okay, any questions on that? All right. When we do rectangular, what's the equation of a line we normally use? Like with our slope and intercept. Do you know that?
Y equals mx plus b.
Yeah, with y equals mx plus b. Now, we know that that's rectangular because there's an x and a y. In polar, do we have an x and a y? Oh, Dylan? No, what is x and y replaced with?
R and theta.
R and theta. Does anyone remember from earlier when we talked about converting a point in rectangular to polar? We had 2 formulas. One to convert the x, one to get the y. Does anyone remember what x equals? Actually, this wasn't rectangular to polar. This was polar to rectangular. Yeah.
R cosine theta.
X was r cosine theta. And how about y? Yeah.
R sine theta.
R sine theta. So now, if we make those 2 substitutions, we can get the equation of a line in polar. So it would be r sine theta equals our slope times Mr. cosine theta plus b. They don't really call it Mr.
Oh.
It's MR. So. And now to graph that, you need to have R by itself. So the first thing we could do is at least get all the R's on the same side. So R sine theta minus MR cosine theta. And now, what do both those terms on the left have in common for factors? Leo?
R.
Yeah, so we can factor out the R. And now the last thing would be to get R by itself. So how would we move what's in parentheses next to the R to the other side? Yeah, divide it. So we get B divided by sine theta minus M cosine theta. That's the equation of a line in polar. Not very nice. So let's say you wanted to graph a line with a y-intercept of, I don't know, 3 and a slope of 2. Just fill in 3 and 2 for m and b, just like you would with y equals mx plus b. So let's try it. So I get r equals 3 divided by sine theta, close parenthesis, minus 2 cosine theta. Now, because I typed in theta, it's important that I let it go through a full cycle. So the cycle for sine and cosine, what's the length of a period? How much? What's the length of a period? For a sine or cosine? In degrees, but in radians? 2 pi. So either way, whatever mode you want to use. I'm in degrees, so I'm going to go with the 360. So it's already all set. I'm going to go by steps of 1. So it's going to plot 360 points to do this. That's way overkill for a line, but it's okay. And let's hit graph and see what we get. So there's one side of the line. And then notice it does the other side of the line. So it's kind of weird the way it draws it. If I zoom out a little more, actually it's still drawing if you look. It's not done yet. So what I'm going to do is I'm going to stop it because I don't know how long that's going to take. And let's speed it up. Let's make our data step 5, and I'm going to zoom out. All right, now I can zoom out. So there's the first part of your line, and there's the second part. So you've got a slope of, what did we say? Slope of 2 and a y-intercept of 3. So definitely doable to draw lines in polar, but it's really, really messy. It's not as nice as y equals mx plus b. All right, so we've looked at circles in polar. We've looked at lines in polar, whether you want it to go through the origin or you just want it to go anywhere, certain slope, certain intercept. Now we're going to look at another shape. This is a more complicated looking graph, so what we're going to do is kind of look at it in pieces. I want to graph r equals 3 plus 3 sine theta. Okay. First of all, if you look at the equation, is the radius staying the same all the time, or is the radius going to be changing in this picture? Yeah, it's changing, right? It's not r equals a number. It's r equals a number plus there's a variable in it. So the radius is changing. So when the radius changes, you don't get a circle. So the first thing I want to kind of focus on is this. If we can figure out what sine is doing, then we can kind of figure out what the radius is doing. Because if we know what sine is, then all we have to do is triple it and add 3, and there's my radius. So let's focus on just sine first. Specifically, we're going to focus on sine from 0 to 2 pi, because that's one full cycle. So here's your graph of sine from 0 to 2 pi. Any questions on that sketch? All right, so for example, if theta was 0, sine of 0 is 0. If theta was pi over 2, the sine of pi over 2 is 1. If we went to pi and plug in sine of pi, we get 0. If you go to 3 pi over 2, plug that in for theta, sine of 3 pi over 2 is -1. And then if we go all the way to 2 pi, the sine of 2 pi, plug that in, we are back at 0. So what I did is I kind of broke that up into 4 sections. The part where it's increasing to its maximum, decreasing till it hits the x-axis, decreasing in green till it hits its lowest point, and then increasing again till it hits the x-axis. Okay, so any questions on that, what I just did there? Okay, so we'll focus on each section one at a time. First, we'll focus on what's happening to the radius between 0 and pi over 2. And then we'll focus on the blue section, the green, and then the black. Right. So let's start with the red section. What's happening from 0 to pi over 2? Okay. So this theta represents the section I'm looking at in sine. I'm going to figure out what's happening to the sine function in that section. And then once I know what's happening to sine, I can take that result, triple it, and add 3. And that'll tell me what's happening to the radius in that section. Okay, so let's start with sine. What's happening to sine as the angle goes from 0 to pi over 2? What's happening to my sine value? It's starting somewhere, and it's ending somewhere. Yeah?
Starting at 0.
It's going to 1. So as the sine function moves from 0 to pi over 2, your value of sine goes from 0 up to its highest, which is 1. Any question on that? So now we know what's happening here. That's going from 0 to 1. All right. So if that's going from 0 to 1, let's see what's happening on the low end and then on the high end. What's 0 times 3? 3, and then plus 3? About the same?
Sorry, what are we trying to find?
So we're trying to figure out what's happening to our radius. We know what's happening to what's in the box. The sine is going from 0 to 1. So my radius is going to go from what to what?
0 to 6.
It's going to go from 0.
Well,
I agree it's going to go to 6. But I don't agree it's going to start at 0.
3 to 6.
3 to 6, yes. So when we make our sketch, in the section from 0 to 90, we have to draw a radius that starts at 3, and as it gets to 90, it grows to 6. Okay, so what that's going to kind of look like, I think I have a graph down here. So when we're at 0 degrees, radius is 3. When we get to 90 degrees, it's growing to 6. So I'm going to put in kind of some radial lines so you can see what's happening, but I'm not going to keep them in, but I just want you to see it. So you start with a radius of 3, and what's happening is as you rotate towards 90, the radius is growing until it hits its maximum at 6. Any question on that? So what it would really look like in this part, it's really hard to draw a good picture, but something kind of like that. Okay, so there's the first part. As you go from 0 to 90, your radius grows from 3 to 6. Okay, let's look at the next section. Now we're going to go from 90 to 180. So now we're trying to figure out what the graph looks like in quadrant 2. What's happening to the value of sine as we go from pi over 2 to pi? That's the blue section. Yeah.
We go from 1 to 0.
The value of sine is going from 1 back to 0. So now we know this part is going from 1 to 0. So now take that result, triple it, and add 3, and that'll tell you what's happening to the radius. So what's going to happen to the radius of our graph in the section from pi over 2 to pi? Yep.
From 6 to 3.
It's going to go from 6 back to 3. And it's basically like a mirror image, okay? Because sine is symmetrical, so is our graph. So it's going to start at 6. It's going to end at 3 by the time you get to 180. And the radial lines are going to kind of go like this. They're going to get shorter and shorter as you're rotating to 180. They get shorter and shorter. All right, so what I'm going to do is I'm just going to take that, try to make my graph look somewhat nice. I'm going to copy it, and I'll just flip it. Okay, it should be a little smoother in there, but that's okay. Okay, so any questions on that one? All right, now let's figure out what's happening in quadrant 3. Let's start with the sine. What's the value of sine going from in the green section? From what to what? Yeah.
0 to
Yep. Here we're going 0 to -1. So now we want to triple that result and add 3 in that order. So what would my radius be going from in this section? Yep.
3 to 0.
It's going from 3 to 0. So what's happening is we get to 270, it's kind of spiraling, it's kind of like going into the origin. Right? Eventually, it's going to hit the origin. So we have the point. You want to think of that as 0, 270 degrees. It's right at the origin. So we start with a radius of 3, and as we rotate, the radii are getting shorter and shorter, until finally, we're just right at the origin. So this section would, try to do it better. Kind of look like that. And then the last section, sine is going from -1 back to 0. So it's just the opposite of what we had before. So our radius is going to increase from 0 to 3. And we end up exactly back where we started. We started with a radius of 3. We've made one revolution. We're back at a radius of 3. So this kind of graph would just continue to trace over itself. And this part would look kind of like that. Now, I kind of exaggerated the shape a little bit in the hope that you would recognize what that kind of looks like. Does anyone kind of see what that looks like a little bit? Is my drawing that bad? I think it kind of looks like it. Anyone have a guess? Please. Yeah, it looks just like a heart, doesn't it? And because it looks so much like a heart, they call that a cardioid. Okay? So the graph in example 6 is a cardioid due to its uncanny heart-like shape. When we draw it on the calculator screen, it's going to look a lot less like a heart. It's actually going to look much more circular than that. So you might see it look almost something like like that. That's what it's going to kind of look like on the screen. But if I drew that, I don't think people would say that that looked like a heart. So I kind of exaggerated it a little bit. Yeah.
So like I drew it on the calculator, and it started at the like 0.3 on the axis, but it didn't go straight up. It almost like bubbled out more. So does that mean between 0 and pi over 2, it went higher than 6 and then went to 6?
No, it can't go beyond 6. 6 would be the maximum distance that this shape ever gets from the origin. Let's graph it. We'll take a look at it too. So basically, anything of that format, where you have a plus or minus a sine theta, we have 3 plus 3 sine theta. That format is called a cardioid. Okay. Obviously, a can't be 0. That would wipe out everything. But theta only has to go from 0 to 2 pi to get a complete graph. If you go beyond 2 pi, you're going to trace over this graph you already have. Okay, let's graph it. So we had 3 plus 3 sine. Was it sine or cosine? Cosine. Right? No, it was sine. If you do cosine, you still get a cardioid kind of shape. I'll show you what happens with that. It just, sine and cosine are phase shifts of each other by 90 degrees. So since sine and cosine are 90 degrees off, if you switch them, it rotates the heart 90 degrees. All right, I'm going to do zoom square because that'll set up that aspect ratio. And I told you it would look more rounded. And may or may not guess that that's a heart, so probably not. Okay. Any questions on that? All right, so there's your shape. If you play with the numbers, like they're supposed to be the same for a cardioid, but if you start to make one different than the other, technically that's not a cardioid anymore, but it kind of smoothed out the, I don't know what you want to call that, the point where it curved back in. And then if you do it the other way, let's make this bigger instead of smaller. I think what happens is it loops back on itself. Yep. So it kind of does like a loop. Yeah. Again, technically that doesn't, it's not a cardioid because it doesn't have the same number in each spot. Now, if you put in cosine, I told you that sine and cosine are just phase shifts by 90 degrees. So it rotates at 90 degrees. If you went from 0 to 180, what's going to happen now? If my theta is only allowed to hit a 180 max. Well, test it. You thought what would happen if theta max only goes to 180? Think of theta, that's like your parameter in parametric. That's like your T-min and T-max. Yeah, what? Yeah, it's going to cut it off. You're only going to get half the picture. It's going to draw from 0 to 180, and that's it. There's your sketch from 0 to 180. Okay. Also, if you don't have your T-step small enough, like let's say you do steps of 20 degrees. So now we're going to go from 0 to 360 in steps of 20. It's not going to look as smooth. I don't know if you can tell from where you're sitting, but I can tell it looks more jagged. Even worse would be if I did something like this. So now it's going to look more jagged, but I also picked a number that's not a multiple of 360, or it doesn't divide into 360. So when we graph it, we're going to get 70 plus 35. You can see the points it's going to graph, but when it gets towards 360, it's going to cut out at 350. So if you look at the cardioid this time, not only does it look kind of blocky, but it also doesn't even connect. Okay. So to avoid that, what did I say to always make sure theta step is?
Can I have that quiz?
Yeah. 1 second. You always want to make sure that your theta step,
Is a multiple of the theta max.
or your theta max is a multiple of your theta step, exactly. So if you do something like 10, perfect. So there's a nice looking cardioid. All right, so just give me 1 second. All right, so any questions on cardioids? All right. All right, so now we're going to take a look at how we can convert an equation that's in polar to rectangular. So in polar, you've got r's and thetas. In rectangular, you have to get x's and y's. Well, we've already got all the formulas to do that right here. If you have an x squared, or if you have, if you've got an r squared and you want to get rid of it, you can do an x squared plus y squared. If you have an r and a theta and you want to get rid of it and it has a cosine, well, we can change it to an x. So we've got formulas here that can relate x's and y's to r's and thetas. So what we're going to do is take the equation of a cardioid and we're going to change it from polar into rectangular. In polar, I think it looks relatively simple. 3 plus 3 sine theta. It's not that bad. Watch what happens when we try to change it to rectangular. It's not even something we're going to be able to draw. Like, we're going to have x's and y's in it, but you'll see from what we do, there's no way you could ever put it in the calculator. Okay. All right, so to convert that to rectangular, we got to get rid of all the x's, all the sines and cosines, and r's and thetas and that stuff. So let's start with this. Let's get rid of sine theta. What could I substitute in for sine theta? Or you know what, even easier question. Out of the 4 formulas, let's call these 1, 2, 3, 4, which formula would allow me to change sine theta and get rid of it? There's only one there that would really apply.
2.
2. We're going to use formula 2, and we're going to substitute in for sine theta. Now, substituting in for sine theta using formula 2, what would you change sine theta to?
Y divided by r.
Y divided by r. So now, at least we got a y in there. That's good, because we're trying to get rectangular. So xy. But we still have some r's. The other thing I don't like that we have now is we have a fraction. So let's try to clear that out a little bit. What could I multiply everything by? So then I just had an equation without any fractions in it. Yep. Yeah, we can multiply everything by r. That looks a little better to me. Now we don't have a fraction. But now it's not in any form. You're mixing y's and r's. It's not polar. It's not rectangular. It's kind of halfway between the two. But look at r squared. What formula could I use up above that would change r squared to x's and y's? Yep.
Formula 3.
Yep. We can make it an x squared plus y squared. So now that side's good. The 3 is fine. And the 3y is fine. The only thing we have to get rid of is r. Well, what formula could I use to substitute in for r that would give me x's and y's? Yep. Yep, you could use formula 3. And using formula 3, what would r equal? I see what you did, but you can't do that. Can you go back a step and just explain how you got what you got, and we'll just stop there.
The square root of x plus y.
Not the square root of x plus y, but we're kind of close. Yeah?
The square root of x squared plus y squared.
Yes. When you have a sum and you want to square root it, you cannot square root each individual thing. So like, if you had the square root of 9 plus, I don't know, 30. You can't take the square root of 9 plus the square root of 30 separate. It just doesn't work. I mean, you can try it. If you have a product, absolutely. If that was 9 times 30, you can definitely take the square root of 9 and get 3, take the square root of 30 separate, and then multiply. So it works fine with a product, doesn't work with addition. So we just leave it. So r is the square root of x squared plus y squared. That's pretty much all we can do. That's the equation of a cardioid in rectangular. Now the reason I said you can't graph it is because to graph it, you have to get y equals. There's no way we're going to really be able to get y by itself there. I mean, you can try, but it's just a mess. If you didn't have this square root with the y squared under it, then you could kind of do something with it because you'd have y squared and a y. It would almost be like a quadratic equation with y. But I just think that square root with the y squared under it is going to mess things up. So that's all you can really do. Okay, so nowhere near as nice looking in rectangular. Any questions on that? So that's how you change from polar to rectangular. So we've done parametric. If I use the names on the calculator screen, we've done parametric to function. We've done function to parametric. We've done polar to function. Now we need to go function to polar. We haven't, it's the only one we haven't done. So this is polar to function. Specifically, what kind of function? Parametric. Okay, we're going to go parametric. Because remember, there's two modes that use an xy axis, function and parametric. All right, so let's just move some stuff out of the way. So I just drew some kind of curve. It doesn't matter how you draw it. You can draw anything you want. Okay, but the point is you've got some kind of curve, and I just marked a single point on the curve. So instead of looking at this entire picture, what I'm basically going to do in my mind is erase everything else, and I'm just going to focus on that dot in black. Because if I can figure out how to represent that single dot in black in parametric, then I can represent any dot that's in black in parametric. But I just have to figure out how to do one of them, and then I can do all of them. All right. So first of all, in polar, what are the two things we're dealing with? Two letters. Yep. So we're going to have r's and thetas. And when we get to parametric, what are we dealing with there? What kind of axis or what kind of grid does parametric use? Okay. It's x's and y's. Yep. So when we get to parametric, we're going to have x's and y's. And keep in mind, what's the letter we always use in parametric for the variable? We don't use, well, I can't really say it without saying it. Yeah, yeah, we're going to use t's. All right, so we're going to go from r's and thetas to kind of these x's, y's, and t's. All right, so let's start with this point right here. That point has a radius. How would you find it? Well, when you write an equation in polar, the formula is r equals. So in polar, you always have a formula for the radius. All you have to do is plug it in. All right. So like if I wanted to know what's the radius of this cardioid, when the angle is 70 degrees. Well, there's the formula right there. To find the radius, plug in 70 degrees, take the sine, triple it, and add 3. And that's the radius. So all you have to do to find your radius is use your equation. So they'd give you some equation in polar, whatever it is, plug in whatever angle you have, and that'll tell you the radius. Now, the other thing you need, besides the radius, you also need to look at the angle. Right? So we're going to be, you don't want to have to deal with an angle in parametric. All right? So we're going to convert that angle right there that I put the arrow for into an x and a y. Okay, and you know what I'm going to do? I'm going to start using the letter we're going to need to in parametric. So I'm kind of running out of space in here. I'm going to call this t. This is my x. This is my y. So what trig function would I use in order to find x, given that I know an angle, which again, I'm calling it t now because I'm getting into parametric, and I should probably even just call this t. In polar, it would be written with theta. So when you get an actual problem, it's going to have a theta in it. But when you rewrite it in parametric, you've got to change the theta to a t. It's just a notation thing. Okay. So what trig function would I use to find x, given that I know an angle and a radius? Yeah? Cosine. So cosine of my angle equals, what's the side adjacent to t? X over my hypotenuse, which is my radius, but I can't just put r because the radius isn't fixed. It's changing according to a formula. What's the formula for the radius? Yeah.
F of t.
F of t. So now to get x by itself, actually I already have it. I'll write it again. So x equals f of t cosine t. It's kind of like the equation of a circle where we had r cosine t in parametric, but r now is a function. The r can change, so it's not always the same value. So there's your parametric equation for x. Does anyone have a guess what it's going to be for y? Let me find this one. Yeah?
F of t sine t equals y.
Yep. So, to kind of summarize it, in polar, they will give you an equation like that. R equals something. R equals 7 sine 2 theta. To write it as parametric, the first thing you have to do is take your function, and you're going to copy it down right there. You're going to copy it down right there. You're going to write it twice. And when you write it, you're going to change the variable to a t. And then to get the x component, to get this component of that point, you use the cosine. To get this component of that point, you use the sine. So it's basically just your function times cosine for the x, your function times sine for the y. And remember, this is your radius. It's just not fixed. It can change. And always use t. Whenever you're in parametric, final answer should be always use t's. Okay, so let's look at this one. So we have the graph r equals 7 sine 2 theta. So they want me to convert it to parametric and then graph it. And I'll graph it both ways. I'll graph the original, and I'll graph what we get, and they should look exactly the same. So anyone think they can tell me the first thing I would write down for x? Yep.
7 sine 2t.
Perfect. 7 sine 2t. And now that 7 sine 2t, what does that really represent? It's the what of a single point on this graph? It's the, exactly, that is the radius. So for once you draw this picture, any point that you draw, that's the radius. So what you basically just found is that. But now, I don't want to know the radius. I want to break the radius into an x and a y component. So how do I get the x component for that radius? What do I have to put after it? Yep.
Cosine t.
Times cosine t. And I don't want just the radius, I want the y component. So how would I get the vertical? Yep. Sine t. And that's how you change something from polar to parametric. That's it. Okay, let's graph what we had in polar. So 7 sine 2 theta. Okay, I'm going to check my window. 0, if I'm doing it in degrees, 0 to 360 is fine. I'm going to do it in steps of 5. And let's just hit graph. I think the x-mins and maxes are fine. And that's the shape you get in polar. So that's the original. Let's put that over there. And we'll just call that one polar. Now let me switch over to parametric and type in what we just came up with. All right, so parametric. 7 sine 2t. I'll go back in a second. 7 sine 2t sine t. And cosine t. If I forget the cosine t, it's not going to look the same. Okay, I want my window to be the same to make a comparison. T-min and T-max, that's not going to work here. If I hit graph, we're not going to get very much. And we're done. So what should I adjust my T-max to? Yeah? So keep in mind, my parameter this time, what is my parameter? It's the what in that expression, because it's inside a trig function. So that makes the parameter and, yeah. Well, it is a variable, but it's inside a trig function. So anything inside a regular trig function is always an, yep, an angle. Okay, T represents an angle. So if you're dealing with an angle, you want to go from 0 full cycle. So 0 to 360. You definitely don't want to go by 0.1s. You're going to watch this graph for about 10 minutes if you do that. Let's go by 5s. And it's not that we made a mistake, we just didn't have the window set right. That's why it didn't look the same at first. Okay, so there's your parametric. And that graph has a special name. Okay, anything of the form r equals a sine 2 theta, it's called a 4-petaled rose. And the length of each petal is the absolute value of the number in front. So our petals had a length of 7 units. If you were to measure it, let's just move this over here. 7 units from here to the tip of the petal. Okay, let's just try something. Instead of 7 sine 2 theta, I'm going to go back to polar. I like drawing these kind of shapes in polar because it's less stuff to type in than parametric. What do you think I would get if I did 4 theta? Guess on how that would change the picture. Get it?
More petals.
Yeah. How many?
Would it be 8?
Yes. You would have 8 petals. As you start to draw more petals, you need to increase your T-step to get the accuracy because there's more sharp curves in it. So that one gave us 8 petals. How about if I did 6 theta? What do you think I would get this time? Leo? 12. So what does the pattern look like? You can start to see the petals are starting to look a little pointy because now I need to increase my T-step. So what's the pattern here to predict the number of petals? Yeah.
2 times theta.
All right, 2 times theta. Let's try this. 3 theta. Let me do one more and then see if we can make a slight refinement to what you just said. That's 5 theta. So can you slightly modify what you just said in order to predict the number of petals? Jane, do you have any thoughts?
What did he say?
Can you repeat what you said?
2 times theta.
2 times theta. So he said it was 2 times theta gives you the number of petals. And it seemed to work for some things. In fact, I showed 3 examples where it worked. But then I showed you 2 where it didn't. You sure? Anyone think they see the pattern? Yeah.
Is it just the odds are equal to the amount of petals? Like
Yep.
it's 3 petals.
So the odds, you get exactly the number of petals you type in. Even, you get double. So that would mean it might be kind of difficult to get something like 6 petals, right? Because if you type 3, you're going to get 3. If you do 4, you're going to get 8. If you do 5, you're going to get 5. And if you do 6, you're going to get 12. So how could you get 6? There is a way. There's all kinds of things you can play with. What would happen if I put it back the way it was and change sine to cosine? What would that do to my graph? Yeah?
You would just move it by 90 degrees.
Exactly. It would rotate at 90 degrees. So now all the petals are going to be on the axes. Okay, that's all that it did. Rotated at 90 degrees. Yeah. So this kind of thing, it's just good to play with it on your own and see what happens when you change stuff, and just experiment and go from there. All right, so 4 petaled rows, we talked about that. Okay, last thing we'll talk about is a spiral. So this is a spiral because the radius is equal to the angle. If you tell me the angle is 90, the radius is 90. If you tell me the angle is 300, the radius is 300. The radius and the angle match. And specifically, we call this one the spiral of Archimedes. So let's put in r equals theta. And I can tell by the mins and maxes they're giving me, they want radians. So let's put it in radians. And now, if I go from 0 to 2 pi, what's the biggest that my radius could ever be? If my theta min is 0 and my theta max is 2 pi. Well, Ken, what do you think my biggest radius would be? Just for the first one, 0 to 2 pi. Yeah, it would be 2 pi. The radius can go exactly as big as you let the angle go, so because they're the same. So when I set my window, at the biggest, my radius is going to be 2 times 3.14, okay, 6.28 units. The biggest part of the spiral, if you draw it this way, is always going to occur on the positive x-axis. So it's going to start here, and as it spirals, that's the furthest point out on the spiral. Okay? When you do another revolution, now that's the furthest point out. So technically, you don't need to go 2 pi on everything, but if you do, you're guaranteed it'll be big enough. So let's go negative 2 pi to 2 pi, and negative 2 pi to 2 pi. Now, what's going to happen is on the right edge of the screen, the spiral is going to be right on the edge, okay, when it gets back around. All right, so I got that. Let's go back to the window and look at it. Think about it. What's wrong here? Why isn't that working? Something's not right. Yeah?
Do you need to change the step?
Yeah, the step is awful. So you're basically trying to graph a spiral using 0, 5, and that's it. So you're only plugging in 2 points to get the spiral. I would probably go by 0.1. Even 0.1, I can tell it's a little jagged, but I can definitely see this a lot better. So there's my spiral. Okay, what would happen if I go from 0 to 4 pi? How's my picture going to change now? Yeah?
Will you just see an extra revolution of the spiral?
Yeah, you're going to see one more revolution. I don't think I need to adjust the y max, because the y max is a pretty short radius for a spiral, but the y min and the x min, you're going to need a lot more space on. So let's go negative 4 pi. And actually, I wasn't worried about the x min, but I already changed it, so that's fine. X max is definitely going to need to change, and so is the y min. Probably could have left the x min alone, and I think I can leave the y min or y max alone. We'll see if it goes off the screen, but I don't think it will. It does. So I need to adjust the y max a little bit. And there's 2 revolutions. If you went 0 to 8 pi, you'd get 4. So a couple of things you could think about is that spiraled inside out. Could you make it spiral from outside in? We could also take the spiral and do something like this. Okay, so I'm not sure if you really noticed the difference, but there is a difference there, and if you graph them at the same time, then you can see it better. It's kind of like some type of mirror image of it. It's kind of like a reflection, but not necessarily left and right or up and down, kind of a combination of both. It's almost like it's been rotated 180 degrees, the spiral. All kinds of different things you can do. So any question on the spiral? And that's just graphing it with negative intervals. I'll let you play with that, and you can see what it looks like if you graph with negative intervals instead of positive. All right, so that pretty much wraps up everything we're going to do on parametric and polar. Okay, so on 493, we've got 19 to 22, 24, 25, 30, 31. And it skips to 33, and then that's 37 to 41, just the odds, and 43 to 49, just the odds. Okay, so because of the superintendent's dinner this evening, there are no after-school activities. So if you do need extra help, we have a little time at the end. Now you could ask me some questions. If you have a study, you could come by, but that's the best we're going to be able to do for this week.